the second mini course, Buzzi will talk about something about the exponents.
Thank you. I would like to thank the organizers for inviting me in Warsaw this month. It's a pleasure to be there. So I will be talking about a joint result with Sylvain and Omri SARIG. Okay. And the structure of the course will be this first week is intended for reviewing all that we need to know about some more or less basic things of smooth ergodic theory. So if you don't know much about smooth ergodic theory, it should be interesting to you. And these are the things that we will need to actually explain to understand the proof of the results. So, yeah, if you have questions, of course, feel free to interrupt. So today I will, this is the plan for the, let's say, the first lecture, the first hour. So I will explain what is the main case of our results. Then I will give you some idea about the proof and how the lectures will be organized. Okay. So what is the setting in this in all these lectures will be of a diffeomorphism on a closed surface. That means compact, boundaryless, and we will strongly use, I mean, not at all time, but at key points, C infinity smoothness. Okay, and invertibility. Okay, we'll be considering the invariant probability measures. Often I will just say measures, but I always thinking about invariant probability measures. And so P of F is the set of those measures. And it is, I always consider it, as usual, equipped with the weak star topology, which makes it into a compact metrizable space. And often I am interested in the subset of ergodic measure. So this erg of F. Okay, I will consider entropy, a number of different kinds of entropies. To state the result, I need the two basic dynamical entropies. The first one is the topological entropy, which counts, in some sense, all orbits. And I will also be considering the entropies of measures, so the Kolmogorov-Sinai entropy for any invariant measure. And the two are connected by the variational principle, which tells you that, okay, the Kolmogorov-Sinai entropy in some sense counts orbits relevant for the given measure. Okay, that when you take the supremum over all measures or all ergodic measures, then in fact you get the same quantity as when you count all the orbits. That's the variational principle written here. Okay, and so I will come back to these things later, but I want to start with the statement of our result. So another thing that we need to talk about is the Lyapunov exponent of a measure. Since we are in dimension 2, there are two Lyapunov exponents, but here it's lambda plus is the largest one, the top Lyapunov exponent. Okay, so these are, I have fixed my diffeomorphism F, and so I have two functions, lambda plus and h, the top Lyapunov exponent and the entropy, defined over the set, the compact set of measures. Okay, we will see that these are upper semi-continuous. Okay, for lambda plus, it's in fact C1 smoothness would suffice. For H, it comes from the C infinity smoothness assumption and Yomdin theory. So they are semi-continuous, but they are not continuous in general, not always. Okay, and for the entropy, it's never the case as soon as it's not this setting, as soon as it's not the zero function. Okay, and for lambda plus, it can be continuous. For instance, if you have an Anosov diffeomorphism, but well, not always. Okay, so now I have rushed a few notions of their names, and I can state our main result, at least the main case. Okay, which is the following. It tells you, okay, you don't have continuity. That's a fact. So now what you can do is, instead of looking at real continuity, you just take a sequence of measures. Okay, in this main case, I assume ergodicity. You take a sequence of ergodic measures nu k, up to passing to a subsequence by compactness. You can assume that it converges to some invariant measure. Now I make an additional assumption, essentially to simplify my life, that the limit is also ergodic. Okay, this is an assumption. Okay, and now let's assume that the entropies of these measures converge. Okay, so and converge to the topological entropy. So these measures see more and more of the dynamics in some sense. Okay, and now I assume also that the topological entropy is positive. Okay, so I assume here I took a sequence of ergodic measure. I assume that it converged. That was not very expensive. I made the more costly assumption that the limit is ergodic. Okay, I assume that the entropy converges. Okay, I could get it by passing to a subsequence, but I assume the main point is that it converges to the topological entropy. So the maximum possible value, and that this maximum possible value is not zero. Then the conclusion is that the Lyapunov exponent must also converge. Okay, so that's the statement. So,
this setting, how many measures of maximal entropy are there?
Okay, so this is what we proved a few years ago, is that in this setting you have finitely many ergodic measures of maximal entropy. Okay, so C infinity smooth surface diffeomorphism with positive topological entropy.
But in this setting, the entropy of mu.
Okay, so in this, since by Yomdin theory, the entropy function is upper semi-continuous, then the limiting measure, this means by definition that the limiting measure has entropy at least as big as the lim sup of these entropies, or here I assume it's a limit. And since it cannot be bigger, then it is equal to the topological entropy. So in this case, this mu is some ergodic measure with maximal entropy. Okay, so this, the reason why we were interested in this statement is that it's a kind of stability result for the measures of maximal entropy. It tells you that in some sense, when you perturb this measure, so instead of looking, so if you're topologically transitive, we prove that you have a unique measure of maximal entropy, for instance. Now, instead of looking at the measure of maximal entropy, you can look at measures which have entropy very close to the topological entropy, so very close to the maximum value. And what this result tells you is that the Lyapunov exponent must be close to the Lyapunov exponent of the MME. So we know, I mean, this was noticed a long time ago, in particular by Katok, that when the entropy is positive, Ruel's inequality, which I will come back to, tells you that you have a positive top Lyapunov exponent. Okay, so you have a kind of hyperbolicity. And this result gives you more. It tells you that, in fact, it's not only true, the Lyapunov exponent is not only positive, but actually, if you perturb the measure in the sense of entropy, the Lyapunov exponent stays close. Okay, so it is something which strengthens the hyperbolicity, the non-uniform hyperbolicity. And actually, what we deduce from that, I will talk about it a little bit more next week, I think, is that is that it gives us a kind of strengthened uniform hyperbolicity, non-uniform hyperbolicity, and in fact we can prove things. So that's a work in preparation also with CROVISIER and SARIG, that, for instance, the MME has exponential decay of correlations. So you should think about this as a stability result for the MME. Okay, in the sense that if you have an ergodic measure with entropy close to the topological entropy, the Lyapunov exponent has to be close to the Lyapunov exponent of the MME. Okay, and it turns out that with further work, using different tools, in fact, we can show that we can deduce from this stability of the Lyapunov exponent some kind of strong non-uniform hyperbolicity, including exponential decay of correlations and other properties of this type. Yes?
If Katok theory, construction of horseshoes, which follow that you have uniform hyperbolic side of entropy laws. And Lyapunov exponent so close, because you just to build this process with typical points.
Yeah.
So it seems that drop down is maybe that it doesn't jump, that the limit is not bigger.
So shadowing result
is the problem here.
tells you that
is bigger.
well, what you know is that it's always proportionally continuous. So the exponent of the limit is bigger than the limit.
This is what I guess.
Yeah, this is we will see once we I recall some definitions and some basic results why this is true. So here what happens is that you actually reach, if so it's not true in general, it's conditional to the fact that the entropies converge, that then you actually you achieve the Lyapunov exponent of the limit. Okay, it's well known that if you have things like homoclinic tangency or near homoclinic tangencies, I don't want to be too specific about that today, you can get measures that approximate some measures. Also, for instance, the one sitting at the periodic point, but in fact it's more general, which have very small Lyapunov exponent.
The limit.
No, I mean the measure that approximate here this limit can be arbitrarily small if you don't have this assumption. Okay, if you just have a weak star, if you just have weak star convergence.
The question is, what is which quality? Greater?
Well, no, it's the fact that it's greater.
This is
That you have upper semi-continuous for very general reasons. Okay, so here the thing is that along such sequences, you also have lower semi-continuity. That is that this limit is not smaller than this number.
the question appears. It doesn't follow.
Okay,
But you will
no, I can answer now. I will answer now. That just tells you can build such a sequence of measures.
Yeah.
What we say is that any sequence of measures that approximate the entropy in this sense, the Lyapunov exponent will converge. Okay, you don't want just the convergence for a specific sequence.
Okay.
You want it for all sequences. In fact, because one of the main application is this strong non-uniform hyperbolicity, which we call stable positive recurrence, for which you need to know that when you perturb the measure, the MME, the exponent stay close. So yeah, so we don't just say that there is such a sequence that would follow in particular from Katok, even in a strong form, since Katok gives you horseshoes.
If we have in Katok, and I wrote it with Sylvain, and a sequence of constructed sequence of sets and any measures on these these sets, but you just choose any sequence.
Yeah, it's for any, it's really kind of stability. You should think about it as stability of the exponent for the MME. Okay, so any other questions? So the way we prove it, that we are going to think about this statement to prove it, is to say, okay, we want to see that if there is, if continuity of the exponent fails, okay, if we don't have our conclusion, then we don't have our assumption, and we don't have our assumption in the sense that we will prove that the limit of these entropies have to be bounded away from the topological entropy. Okay, this is just essentially contradicting the statement. It's proof by contradiction. So this is what we are going to prove something a little bit stronger, a little bit more quantitative than just saying we are bounded away from the topological entropy. We are going to say that if the limit of the Lyapunov exponent is equal to beta, to some number beta times the exponent of the limiting measure. Okay, upper semi-continuity tells us that beta is less than 1. Then, and that these numbers are positive. Then, actually, we can bound the entropy of the measure nu k by beta times the topological entropy. So if I know that this limit is equal to the topological entropy, then beta must be equal to 1, and I have my result. Okay, but this is the way we think about it, that if we have a failure of continuity of the exponent, it gives us a non-trivial bound on the entropy of the measures in UK. Okay? So we can split the proof into two.
Lambda less than 1?
Beta, okay.
Lambda plus. If lim lambda plus equal beta times, my question is what is beta?
Oh, beta is some number.
But it can be bigger than 1? Or?
No, upper semi-continuity tells you that beta is less than 1.
Okay.
Since these things are positive, beta is non-negative. Actually, it cannot be 0. Well, this tells you that beta is not equal to 0. So beta is positive and at most equal to 1. Oh, this is an assumption. If
Right, but you said that you are going to think about it in this way. It seems that you also need.
I think about it in a very strong way, sorry. That's not fair. Sorry, so what I should have said here, okay, that there is a typo here, it's the lim sup. Here I should say the lim sup. But this is why I have the paper. Okay, so here is the lim sup. I don't know that this limit exists, of course. Okay, really it's an entropy bound. So I'm going to say, okay, if the Lyapunov exponent do not converge to the exponent of the limit, then this means that this number beta is less than 1, and I get that the lim sup satisfies a non-trivial bound. Does that answer your question?
Could you please repeat?
No problem. I could tell you something that Mark Policott once told me, but I will tell you in private. Okay, that it's okay. What I'm saying is that if you have this assumption, okay, if beta equal to 1, then you're happy. Okay, it means that the Lyapunov exponent converge. So by contradiction, you assume that beta is less than 1. And it gives you that the lim sup of these entropies is bounded away from the topological entropy. So it's a proof by contradiction of the other statement. Does this answer your question? You look puzzled.
So how did you solve the issue of convergence, that the limit exists?
Which one? This one? This one?
With the original, so let's say that the proof by contradiction, in the first case, the limit doesn't exist.
The limit of what?
The boundary.
So this is
not in this term, in the original.
Let's understand why this proves the contrapositive.
yeah, it's
So let us
the assumption is that you have the limit exists and is equal to the topological entropy, which is positive.
that's the assumption. Now let's assume that
So we assume that we have this assumption. Well, and we don't have the conclusion.
we don't have the conclusion.
So the conclusion, okay, so then the conclusion is that, well, so first we can make the limit exist just by willing it strongly, or if you prefer, using compactness of bounded intervals of real numbers. So this is a real number which will be between 0 and the log of the Lipschitz constant of F. So if it's you can, if it does not, well, whether it converges or not, it has accumulation points. Okay, so it's enough to show that this is the only accumulation point possible. Okay, so here you consider you take a subsequence, you see any accumulation points, you see if there is one that would not be equal to what you want. Okay, so anyway, any accumulation point has to be of this form because of upper semi-continuity. It cannot be more than this number, okay, and it has to be non-negative. So it has to be of this form up to going to a subsequence. And then here I should say that the lim sup is less than my bound. Okay, so really so what you see here is that what we are doing, the whole business will be showing that if you have a defect in continuity in this sense, that beta is less than 1, then you get a non-trivial entropy bound. Okay, and if we have this, we have the main the statement I gave before. Okay. So how can we prove such an entropy bound? So first we look at the differential. I mean, as I will recall soon, the Lyapunov exponent is the growth rate of the differential when you iterate. So you want to understand it, and a well-known trick to understand these Lyapunov exponents is to consider the projective dynamics or the dynamics on the projectivization of the tangent bundle, which is just this extension of the dieomorphism F, where you consider not only points, but points with direction. So here E ranges over the one-dimensional vector subspace of the tangent space at X. Okay, and you apply the map that you have, which is the differential of F at X. Okay, and what we will see by applying classical results or basic formulas from Furstenberg, Laudrapier, that kind of people, is that the discontinuity of exponent will correspond to some kind of homoclinic tangency. So that we will have that for a fraction of the time, the unstable direction becomes aligned with the stable direction, and you don't get, you have large time intervals. Sorry. Okay, which we call neutral blocks, where you don't have expansion at all. Okay, and expansion at all. So in some sense, you get discontinuity of the Lyapunov exponent because you have this phenomenon. Okay, this is what we will see by looking at what is the meaning of the discontinuity on the projective dynamics. We will see that we have this time interval without expansion for the differential. Okay, this what we will call the neutral blocks. Okay, and for actually time which will be related to this beta. So this is for the differential. Okay, the tangent dynamics. Now we want to use it to get our entropy bound. So the entropy is not only about what happens for the differential. Okay, it turns out that, so what we look at are parametrized curves in the spirit of Yomdin theory. Okay, and there is a kind of routine bound, which is that okay, the growth we are interested in is bounded by the topological entropy. This is more or less exactly Yomdin theory. Okay, we can refine it in some cases. I don't want to talk about it now. And then the central point of the proof, where really we have to work, is what happens during a neutral block. Okay, which correspond to time intervals where the differential in the unstable direction, in what should be the unstable direction, is actually contracting. Okay, so here we have to extend this contraction for the differential to a contraction on the curve, say, showing that the curve doesn't grow and that, then this will give you times during which there is no entropy creation, and this will give us this factor beta less than 1. So to do that, we use, as soon as we want to deal with curves, we have to use Yomdin theory. Okay, and now the problem that we have is that we know that the differential is not expanding, and we want to use this information to say that the curve is not expanding locally. So to do that, well, one thing that appears, well, is certainly if the tangent to the curve is almost constant, then it's a reasonable conclusion to hope that the curve also will not grow. This small piece of curve will not grow. Okay, but then then there is a catch, which is that, well, you need to enforce this fact or this wish that the tangent to the curve is almost constant. Okay, but now the neutral block only tells you that the curve does not expand. It tells you nothing about the direction of the curve. Okay, so to control this direction of the curve and to see that as you iterate, it stays, that the direction of the curve stays almost constant, we will need to use the fact that we are looking at the unstable direction and that this is a measurable function over the space. Okay, so we will work. I warn you, this is the part where things get complicated. But at the end of the day, what we get is that most of the time, this measurable function looks like a continuous function. That's a usual trick in measure theory. And now, so if we have a continuous function, it tells us that if we know that we control the points on the surface, if we control them enough, it will control the direction of the curve in the image, so that we are in a good shape to iterate. Because at the next step, we want again to be able to say we are still in the neutral block, and the direction of the tangent of the curve being almost constant, we can use the information from the differential to say that the curve doesn't grow. Okay, but when we do that, we have a problem, which is that we need to control the point on the surface, the base point, at a much smaller scale, because we are using the modulus of continuity of this unstable direction. And there is no reason why this modulus of continuity is good. In fact, we are approximating a measurable function, so probably it's not good at all. So we need a scale on the surface, which is much smaller than what we need on the projective bundle. Okay, so this will lead to the introduction of this double scale. Okay, anyway, that's where you suffer, or at least I. And you conclude, so what we want to do is to bound the entropies of these measures for K large. Okay, and for this, we use a formula for the entropy that tells us that that essentially it's enough to look at unstable curve in the sense of Casing theory. So I will go back to all these things at length.
Yomdin proof also?
So there is, well, it's an idea which appears in several forms in the work of several people. In dimension 2 especially, it goes back to at least to Young, to a paper of Young, Lesson Young of 1981. Yeah, in Newhouse, there is maybe you are thinking of an application of Yomdin theory by Newhouse, where it's a little bit different. It's related also.
My question was whether you will go deeper into Yomdin proof.
Yes.
You are. Okay.
So that's for the next.
Where you will explain us Yomdin.
Yeah, this is okay. This was some kind of I don't know how to say some terrorism attempt. So here I gave you in I don't know 10 minutes, 15 minutes what will take me 2 weeks to explain. Okay, so I'm not pretending. I don't think that. Don't dare to think that I have been here. It's just to give you a kind of global picture so that you have some idea about where we are going. Okay, but of course, this was very quick and I threw a lot of words without really explaining anything. So here is more or less the plan. Well, certainly I won't be able to stick to it in the details. So this first week, so today and Friday, I will review some facts about the Lyapunov exponent entropy. Then I will essentially, by just quoting definitions and theorems, then I will explain Yomdin theory, which we need mainly for curves. Okay, and it turns out that for curves, well, you can expect it for curves, it's much simpler. And if I don't get lost, I will be able to, if not give you a complete proof, at least give you a complete proof of the core lemma that makes Yomdin theory work when you're looking at curves. Okay, then you need more technology to get what you want from it. But I hope that I will be able to convince you that this is the lemma that you want, and we will see that in dimension 1 it is quite simple once you know what you want to do. Okay, and so that will be essentially reviewing basic things, and then I will introduce these neutral blocks either at the end of this week or at the beginning of the next week. I will explain how we implement this double scaling. Okay, essentially we have to go back to all what we did this week and replace epsilon by a couple of numbers. And then the core part is this to control what happens to the parameterized curve when you are inside a neutral block. Okay, this will take a lot of time. Once we have this, it will be quite easy to explain how to deduce from that the main theorem, the main case of the theorem that I gave you a moment before. And I will not prove, but just tell you about the kind of properties that we can get from once we have this convergence of the Lyapunov exponent. Okay, this strong and non-uniform hyperbolicity that we call strong positive recurrence, or SPR. And if I have the time, I will then give you the general case of our results, where we don't assume that the entropy, that you converge to the topological entropy, that just that you converge to some measure. Okay, and this case, okay, it gives you, in particular, this is, it has application to the existence of SRB measure. So, well, if we are very lucky, I will get to that. If not, I will, maybe I will not talk about that, or I will just give you the general statement. Okay, that's the plan. Essentially, this first week to review what we need from Lyapunov and entropy theory. And next week, actually prove our entropy bound. Okay? So I will give the slides, so this you don't have to. This is okay. So this is based on this paper. I mean, the whole course is based on it. It's trying to explain this paper, and here you have these 3 books about which give you some background, and then there are other papers that are related to these problems. Okay, especially by David Kurget. Okay, so yeah, maybe, so I state the exercise and maybe we take a break. Is it good? Okay, so the exercise for you is the following. So I made this statement, the main case of our result, where we assume the ergodicity, and now we want to remove the ergodicity assumptions. Okay, and what the exercise is to see that using the spectral decomposition that we proved in an earlier work, so with Sylvain and Omri, we can do that, you can do that. Okay, so what is the spectral decomposition? It's to say that if we are in our setting, so you have a infinity smooth surface dieomorphism, you can find a family of invariant compact set, which I call here Ki, which have the following properties. Okay, so if you look at any ergodic measure, it is with positive entropy, it is carried by one of the Ki. Okay, that's the first thing. Each Ki has a unique measure that maximizes the entropy in itself. Okay, and you have this kind of quasi-finiteness. If you fix a positive threshold, the number of Ki that have topological entropy bigger than that threshold is finite. Okay, so the exercise is to use this decomposition to see that once you have the main case of the theorem, where you assume that you have a sequence of ergodic measures converging to an ergodic limit with entropy going to the topological entropy, then in fact you can just forget about ergodicity and get this stronger statement that if you have a sequence of measure, converging sequence of measure such that the entropy converge to the topological entropy. Okay, then the Lyapunov exponent also converges. Okay, that's the exercise. And then we take a break. I don't know how long.
Yes.
You have to give an explicit bound of the break.
10 minutes.
Other questions?
Continue to the second part.
Thank you. So, okay, so now so after this kind of review of where we are going, I'm going to get back to basics, and especially about what I need to know, what we need to know about Lyapunov exponents. Okay, so we'll see how they are related to matrix norms, then to what happens to vectors, what Kirsten can tell us about the dynamics, and finally this business about projective dynamics, and how can we understand in a positive way the failure of continuity of the exponents. Okay, so, well, I don't know why this appears like that. Anyway. So, definition. So here we only need C1. Okay, and for this part, we could be in higher dimension. We don't care. We are compact, boundaryless. So the top Lyapunov, the average top Lyapunov exponent of an invariant measure is the following limit. Okay, where you take the norm of the differential of the n-theta rate. Okay, you take the log, you average, you divide by n, and you try to find a limit. Okay, if this limit exists, you call this the average top Lyapunov exponent, or just the top Lyapunov exponent of a measure. Okay, now you have a pointwise top Lyapunov exponent, which is the same kind of quantity, but you look just along one orbit. Okay, maybe it exists, maybe it doesn't exist. Okay, if it exists, this is what I call lambda plus of x, and the first one was lambda plus of mu. Okay, and now how do I understand these things? Okay, the fundamental remark is that the function which to x and n associate the logarithm of the norm of this linear operator is a subadditive process, okay, which means exactly this, that you have this inequality. In fact, it's even a bounded, it's also bounded. And so we can apply Kingman's ergodic theorem, okay, which tells us exactly that this average top Lyapunov exponent does exist. And in fact, it is given, it is not only the limit when n goes to infinity of this average, but it is the infimum of these things. Okay, and it is what it should be. It's the average of the pointwise Lyapunov exponent, which exists. So this quantity, it's not at all clear that it exists. Well, it usually does not exist everywhere, but by this ergodic theorem, it exists almost everywhere. Once you know that it exists, it is clearly F invariant. I'm dealing with a dieomorphism. Okay, and then the conclusion is that it's the average Lyapunov exponent is indeed the average of the pointwise exponents. Any question about that? Okay, so that's.
No, well, I would prefer the top formula one and the same, easier to compare this line with the next one.
Yeah, it's just I felt that writing it that way, but there is no clearly the theorem tells you that
before everything.
yeah, you it's well, they are the same. Okay, and now so one immediate consequence of this formula is what we have been talking about for a long time, which is that this average exponent is upper semi-continuous. Okay, and this is now direct just because it is an infimum of continuous functions. I mean, the definition of the weak star topology exactly tells you that these functions, this is a continuous function of the measure. Okay, since this is a continuous function of the point. Okay, so we have this upper semi-continuity for the exponent as soon as we are C1 on a compact guy. And now, a second exercise, you can look at the bottom exponent, okay, average and pointwise, which is just defined as minus the top exponent for the inverse map. Okay, and then exercise, check what it gives to you. Okay, indication it will not be a semi-continuous. Okay, but that's just to have some fun. Question? Okay, so we have these two bottom and top exponents. Okay, now we are back on a surface, and we want to understand our exponents much more precisely in a much more geometric way using Osseledet's theorem. So we are back in dimension 2, and we're considering this projective tangent bundle a first time. Okay, I just give the definition here. You have over each point, you have the set of all one-dimensional subspaces. Okay, so it's a nice bundle. And now Osseledet's theorem tells you this, that you have disjoint invariant Borel sets. Okay, this X0 and X sharp. And over the second one, you have measurable section, that is measurable maps from this subset of M to the projective bundle. Okay, with the following, so section means it's a measurable map, and it sends X to direction over X. Okay, so first, these two sets together have full measure. Okay, the first set is essentially up to some set of measure 0, where the Lyapunov exponents, the pointwise Lyapunov exponents are defined and equal, and X sharp are where they are defined and not equal. Okay, depending on the measure. So these are invariant set if the measure is ergodic. Okay, sorry, I forgot to say. This is for any measure. So you have these two Borel sets. And now for any measure mu, you have these properties. Okay, that the two sets together have full measure. Okay, for all points in the first set, all non-zero vectors grow at this common rate, which is the common value of the two exponents. Okay, this means that you can, I don't know, if this value is positive, it means that it grows exponentially in the future and it shrinks exponentially in the past. Okay, and on the other side, it's more interesting. You have, so if you take any vector along E plus, the non-zero vector, then it will grow at the rate, exponential rate given by lambda plus. Okay, same thing, you can iterate forward or backward. Okay, that's for, you have this property for E plus with lambda plus, for E minus with lambda minus. Okay, and now the two directions, okay, of course, because of this property and the fact that from X sharp, the two exponents are distinct, you know that the two one-dimensional directions must be transverse. I mean, their sum is the tangent space X. So, but they have some angle between them, always positive over X sharp. But this angle doesn't grow too fast when you move along an orbit. Okay, in the future or in the past, I mean, here everything is invertible. So you have this property. Any questions? Okay, so this is well, Kingman's ergodic theorem is not trivial. Okay, Osseled's theorem is harder, but okay. I will not say more. Okay, exercise. Okay, we have seen that, or at least I have said that these lambda plus, lambda minus are not a continuous function. But now if you take their sum, you can check that this is a continuous function of the measure. Okay. So the title is wrong. Sorry? George? Okay, so really it tells you that the two, when you have two distinct Lyapunov exponents, it corresponds to two directions which are expanded at a different rate. And things in the past look like things in the future. Okay, so this is what you should expect, but still someone has to prove it. Okay, so now, sorry, it's about hyperbolicity in the sense of Pearson. So I will say that a measure is Pearson hyperbolic, sometimes just hyperbolic, if for almost every point, the top pointwise exponent is positive and the bottom pointwise exponent is negative. Okay, and now if you have such a measure for almost every point, you can look at the stable, well, okay, at this set, which is the set of points whose orbit converge exponentially fast to the orbit of X. Okay, and Pearson tells you that this set is not some kind of horrible set, it's a curve. Well, more precisely, it's an immersed curve. Some settings can be dense, for instance, which is as smooth as F, and which is tangent to the stable space given by Osseled's theorem. So the direction where vectors are contracted by the differential. Yeah, I say contracting because here my assumption is that lambda minus is negative. Okay, and as usual, if you can define something stable, you can define something unstable just by looking at the inverse. So this means the points that converge exponentially fast when you iterate backwards. Okay, so this is a generalization of what you have for uniformly hyperbolic sets. Okay, but this time it's for measures, just assuming this asymptotic property about in terms of the exponents. Any question? Okay, so now we go to our projective business on surfaces. So, yeah, so one thing that you can check as an easy consequence of Osseled's theorem is that the top Lyapunov exponent is just the average of this function. Okay, the logarithm of the, so here E plus Okay, so sorry, so I didn't write it, but I am assuming here that mu lives on X sharp, otherwise what I'm writing makes no sense, sorry. Yeah, I need to.
What is mu?
So mu, yeah, you're right, I forgot to. So in the exercise, mu is an invariant measure, and we have to assume that it lives on the set where I have two distinct exponents, and therefore, by Oscillated's theorem, I have two directions, e plus of x and e minus of x, almost well, on this set, so almost everywhere. And then then I have for mu almost every x, I have that e plus x is one-dimensional.
Oh, no, I just want on the right, you have x plus.
Sorry, yes, sorry, I wanted to, yeah, so you're right, this should be E plus. This should be E plus. Okay, so it should be the integral of the logarithm of the norm of the restriction of the differential. So I didn't say it, I should have said to define all the Lyapunov exponent, I need to equip M with an arbitrary Riemannian structure. And when I define here I have these norms. Actually, even before I use the norm is understood. This is so this is a vector in the tangent space over Fn of x. So I'm using the norm given by the Euclidean, by the Riemannian structure at this point. Okay, so I need to have a Riemannian structure. Okay, and you can check exercise if you like that the value of the exponent do not depend on the choice of the Riemannian structure. For instance, because I am compact here, so it makes it doesn't change anything. Are there any questions about that? Sorry.
Next slide.
Okay, so here, this should be the distance corresponding to the Riemannian structure. Let's say the geodesic distance. Yeah, sorry.
Everything is the same.
Oh, it's really, well, you can think already about the case of an ergodic, of a hyperbolic automorphism of the torus, so another dieomorphism, and then each stable manifold will be a line, an infinite line, which is dense on the torus.
Or typical C infinity, if you want. Is it?
Well, I don't know. I mean, then it can, all kind, what this theorem tells you is that there is some scale which depends on some controlled way, but that can get arbitrarily small, where you have a piece of the manifold which looks in a fixed chart very close to a straight line. Okay, but the scale where you have this, you have no real control about it. Well, actually, in some sense, what we are fighting for is to have this control. But that's a very long story. So in principle, here in casing theory, you don't really know. You will just know that it's there is such a scale, and that it doesn't shrink exponentially fast. Okay, along orbits, and in casing theory, that's about everything, all that you know about. Okay, so the scale can be the scale where it is in a fixed chart close to a straight line can be very small. And then what happens when you iterate is, well, I don't really know. But what we know is that already in very good cases, it can be dense, it can accumulate on itself or on many things. So locally, it has a very simple structure, but then globally, it is complicated. That's the idea. And okay, sorry. So I go back to the exercise. So what we have, if we use Olmsted-Hedges theorem for a measure which lives like that, okay? Yeah, I realize now that I should formulate this differently, but let's pretend that I don't see the problem, that you have that the top Lyapunov exponent is an average of some function. Okay, since this is a one-dimensional, I can just have a value for the empirical particle about the norm, or it's the same thing as the Jacobian, because these things are one-dimensional. Okay, but what cannot be in general is that this coincides with some average of a continuous function. Okay, so I mean simply because otherwise it would be saying that the lambda plus is a continuous function. Okay, and I said it is not, and you believe what I do. Okay, so now now the projective bundle is a way to recover the exponent as the integral of a continuous function, but not defined on M, but defined on this bundle. Okay, so the bundle is what I already introduced. It projects in this obvious way to the surface. The dynamics is also what I introduced. So this I will write it F hat. It's just on the point I apply F, and on the subspace I apply what I can, that is the differential. Okay, and now I have an extra information, which is the direction. Okay, when I was on the surface, I didn't really know the direction in which direction. So I had to use, for instance, the unstable direction from Olmsted-Hedges theorem. This was only a measurable function. Okay, here on well, I have done everything. This is why people look at the tangent bundle. Here you have a direction, so you can define this direction, and it is a continuous function. I mean, these things have been built for that. Okay, so it's a smooth bundle, it is compact. Since it is a compact bundle with continuous projection, all measures can be lifted to the bundle. Okay? Sorry?
The bigger is smaller.
So here, well,
The definition of the differential.
oh, sorry, yes, it's a small f, there is no big F. Thank you. That's me. Okay, so every invariant measure for F on the surface can be lifted to an invariant measure for the projective dynamics. I mean, just in this general setting, you have this. If you wish, you get a generic point below, and you construct from that an invariant measure above, which will have to project to the measure below that you selected. So you have everything can be lifted. Okay, and since measure above, if it projects to a non-ergodic measure below on the surface, it must be non-ergodic. Therefore, this projection, this is to say that the projection respects, if you, the ergodic measures here, they lift any ergodic guy on the surface lifts to an ergodic, can be lifted to an ergodic guy on the tangent, on the projected button. Okay, so of course, since the dilation is continuous, okay, we just apply the definition of the weak star topology for the invariant probability measure for f hat. You see that it will, these quantities will converge. And the last easy fact is that the dilation, well, we are right to call it dilation, since it exactly gives you by which factor a vector is dilated. When you apply and iterate of the map, you see the Birkhoff sum of the dilation appear. Yeah. Okay, so that's just to.
Let me ask you.
Yes. Yes.
So you assume the law of differential is not continuous?
Well, no, the differential is continuous. You are infinity, so in fact you are at least one. But what is not continuous is the direction.
You assume.
No, I don't assume. The direction here, okay. So when I wrote this stupid formula, I forgot that E plus is not defined everywhere. Okay, but apart from that, so if you add this assumption, Osseled's theorem gives you a measure of a direction.
Sometimes it is continuous.
Yeah, sometimes it is continuous.
So you say in general.
It cannot be, yeah, you're right. Yeah, it cannot always be written. So in general, of course, I mean, for instance, if you have a uniquely ergodic system, then certainly everything is continuous. Since okay, fine. But so yeah, I should have been more careful. Okay, so let's forget about this exercise. Okay, exercise, write the exercise correctly. Okay, so now so I have said that we can lift any measure. We can also lift any ergodic measure. We can choose an ergodic lift. Now we want to understand these things more precisely. Okay, so the first thing we want to understand is that the top and bottom average exponents are exactly the averages of the dilation. Sorry, there should be a hat. Mu. So there should be a hat here. So to get the top and bottom Lyapunov exponent, what you have is exactly the averages of the dilation with respect to the ergodic lifts of your measure. Okay, so why is this true? Let me so the proof, or at least the key remark of this remark, is the fact that, okay, according to Osseled's theorem, we know that for mu, almost every point on the surface, Okay, the set of values for this growth rate for any tangent non-zero vector. Well, if you look back at the Selected theorem, we only got two possible values. For the pointwise, for this pointwise, for this growth rate. Okay? Over a set of full measures. And now, if you have an ergodic lift, okay, as in the statement, then what happens is that well, you can apply Birkhoff's theorem. To see that the possible values of the averages of the average, I fix mu hat, there is only one average, has to be, well, Birkhoff tell you, it's the almost everywhere value of the pointwise average. So this certainly belongs, this gives you one equation. Okay, so that we get the first half of the first point, and now we are going to complete the proof by proving the second point at the same time. Okay, so first, let me say that if there are two cases, let's say case 0 is if the two exponents are equal. Okay, then there is nothing more to show. Okay, we are done since we have shown that the possible value for the average is the common value of the top and the bottom exponent. Okay, it has to be some value. So one is proved in the case where the two Lyapunov exponent converges, where the two Lyapunov exponents converge. Okay, is it clear in this case? Yeah, now, can I write also on the other side? So now, this is the case where we have distinct exponents. Now what I'm going to delay this and say consider the two measures defined here. So what am I saying is that I am in this case, mu is ergodic. So this tells me that mu is carried by the set X sharp from Osseledet's theorem. Therefore, almost everywhere I have this function E plus of X and E minus of X. Let's focus on X plus. Okay, let me focus on this.
Do you call X sharp X1?
Then, yeah. Okay. Yeah, it should be. Yes, you're definitely right. That's. I wrote it first X0 and X1, and then I saw that X sharp was so much cooler. Well, that was you asked her for postcard. I don't think she covers enough for my typos. Okay, so let's focus on this. So anyway, this is a full measure set. So here what we are saying is that we have an invariant, we have an equivariant function. Okay, so first, this is defined almost everywhere. It is equivariant. So df of, okay, let me write it, df has to be plus at f of x. Therefore, let me introduce it well. Therefore, this mu hat plus, which is a lift of mu on the graph of this equivariant function, is invariant. Okay, since it's a lift on a graph, it's automatically ergodic. Okay, because if I had an invariant, if I take an invariant subset in the tangent bundle, in the projective bundle, okay, I map it, but the map on the graph is of course 1-to-1, so I get an invariant subset on the surface, which has to have the same measure for mu as the subset above had for this mu hat plus. So if this guy was not ergodic, mu would not be ergodic either. Okay, so now, and clearly, the average of the dilation is, well, will be exactly this log of which is not that words of mu.
You will get therefore you have close lift of mu.
Is as a lift on the graph of this function is invariant for okay, if you wish, I can introduce the graph itself. I mean, and now what I'm saying is that the equivariance here exactly tells me that this graph is invariant. F hat of gamma plus is equal to gamma plus. Right? It is exactly well rewriting this equivariance. Okay, therefore the set here is invariant. In the same way, you can show that since mu is invariant by f, its lift by any invariant graph is again an invariant measure which has to be ergodic if the one below was ergodic. Okay, this is true as soon as you are lifting to an equivariant graph. Okay, so now what have I done? I took a measure mu with distinct exponent. Okay, and I constructed a lift on the unstable directions. Okay, on this graph, gamma plus. Okay, which is ergodic. And now I was able to see that the average of the dilation with respect to this lift is the top Lyapunov exponent. Okay, just by putting what I have. Okay, this is a log of df at xe for d mu hat plus, and now for mu hat plus, E is equal to E plus of X. Okay, so I have this equality, and by the first exercise, it's equal to the top Lyapunov exponent. Okay, so what I'm saying is that Oscillator's theorem gives us an invariant section, the unstable section. Okay, once I have an unstable section, once I have an invariant section, in fact, I can lift a measure, an invariant measure to an invariant measure, and if the measure I start with is ergodic, the lift will be ergodic. I mean, the measure will be, in fact, isomorphic. It's just by a graph. Okay, and now this is not only an ergodic lift, but it gives me the top Lyapunov exponent. Okay, so I had the inclusion. Okay, and now I have seen that I have shown that the value lambda plus of mu is indeed realized. Okay, of course, what I've done, I can construct a lift to the stable section, okay, defined by E minus of X. Okay, and it will give me, it will be in the same way, or exactly the same reason, if you wish, replace F by F minus, to see that it gives you an invariant ergodic measure for the bundle dynamics, the projective dynamics, and the average of the variation this time is the bottom Lyapunov exponent. Okay, so I have realized, I have shown that for ergodic lifts of my ergodic measure mu, okay, I will obtain exactly the two values of the two exponents when I am in this case sharp, where the two exponents of mu are distinct. Okay, so this proves the lemma. That is describes all the possible ergodic lifts if I start from an ergodic measure. Okay, this is especially simple because we are in dimension 2, and therefore either every direction behaves the same when the Lyapunov exponents are equal, or I just have one stable direction and one expanding direction, and there is no possibility of rotation inside a two-dimensional space or whatever frightening you might think of. Here it's just that. Okay, so these lemma are classical, of course. Yes?
How do you see there is no other?
There is no
Other. Right, so then it's exactly two ergodic.
Oh, so here, what so I didn't, oh yeah, you're right. Well, you have to look at it more. Let me think about, yeah, you're right. I showed that these were the two possible values for the average. I didn't show that these are the only possible ergodic lift. Okay, this is a little bit subtler. I will do it next time. It has to involve the fact that if you come back very close, you see that either you are in the stable direction and you come back exactly as the stable direction by invariance, or you are transverse to the stable direction. And then when you come back, you have to be very close to the unstable direction. Okay, using Oscillator's theorem. Okay, and this is what will get you that these are the only two possibilities.
Because we can pose each vector on each point on the project space on a sun as a stable direction.
Yes, and you have, I didn't write it, I should have.
And push to the
Exactly, thank you. So I could have written that somewhere. I don't know if you can say it. And as she said, yeah, this is, you have this, and okay, if you're not aligned with the stable direction, if you come back very close by using recurrence, you have to have become extremely close after time long enough, extremely close to the stable direction. Okay, so from that remark, you can show that these are the only lifts. Sorry. So I see that I have to. Okay, so that's one. So this is when the measure on the surface is ergodic. When it's not ergodic, okay, I will use this fact, assuming that I have distinct Lyapunov exponents almost everywhere. So in some sense, if I was ergodic, I would be in this second case. And what I'm saying is that, well, I can just look at the ergodic decomposition. Okay, almost every ergodic component will satisfy the assumption of case 2 here. Okay, and we'll have therefore the two unstable and stable lifts. And what I'm saying here is that, okay, each time you give me a measure, a measurable function, okay, with values between 0 and 1, I can just build a lift by taking these averages, and that these are the only lifts possible. Okay, so this, fortunately, I don't have the time to prove it. Okay, so here today, well, I'm just, so this is what we said, and actually, X1 is still X sharp. Okay, that any measure which has this property of distinct pointwise exponents almost everywhere, all its lifts lived on the union of these two graphs, the stable and the unstable graph. Okay, and if we restrict, so in principle, if the measure is not ergodic, it could be the lifts are average of stable and unstable lifts for each ergodic component. But if you know for some reason that you are living inside one of these invariant graphs, then you have unique lift, not just because it is a graph. That's just a rewarding of what we said before. Okay, maybe I should stop. Sorry? Okay, so